All right, so welcome everybody to today's lecture. The topic is binarization in neural networks, which is a pretty interesting topic for the applications that it allows us to entertain. So I'm going to spend some time at the beginning with motivation. So a little bit about all the storage power and computation that is involved in training and using a neural network for inference, and then set the stage that, if you want to apply any of these things on what's called edge devices, edge is, the term used to say that you're like at the edge of the cloud, you're really on one of those, battery operated devices like a mobile phone, like a GPS device or something, of that nature. And these devices are pretty restricted in all of these aspects. So the way forward there is this, topic called quantization that has been developed from different fields, and in the context of neural networks, it essentially means reducing the precision of your numbers, the numbers that you're storing. So we'll see a little bit about floating point numbers, how they get finicky in certain aspects, and some pros and cons. And then move on to BNNs themselves, binary neural networks, see the core concepts, basic model, and then some improvements over the original models that have been developed over the years. So let's begin then with the motivation, setting the stage. Like I was saying, deep neural networks, they do a lot of number crunching. They are pretty energy hungry. Here we can see a timeline. Here it's pretty interesting to see, how it all started in the 40s. The first neural network was just, around 10 neurons. Then in the 80s, we already had the one of the first, bigger ones that was around 20K neurons already. So this is for those of you who thought that neural networks were the, really new from this century. And then from there, it started really growing until today. We have some models with over a trillion, more than like 1.6 trillion neurons. So this is pretty, it's a pretty huge number. So to realize what this means, really, let's stop for a minute and say, let's see what all of the computations that go on in the model. So let's take CNNs, convolutional neural networks. They typically have many layers. They can have more than 100 easily for large pipelines, especially with self-learning feature extractors. Their running time is dominated by what's called multiply accumulate operations. It's around 75 to 85% can be assigned to these sorts of operations. We'll see what this means in just a second. And there's also significant traffic between layers, so you have to move up to 200 megabytes per layer easily. So this graphic here shows a little bit about what's going on. The convolution has to take, for each channel, you have to do this, do an operation, then you have pooling, and then you have, all the fully connected layers, and then you get your result, in this case, correctly classifying the image as a 5. So for the most well-known data sets, MNIST, CFAR, and this other one, you have, different numbers of classes, but let's look at the image sizes. You have for MNIST and for CFAR, they're pretty small, 28 and 32 times like a square. And then MNIST is black and white, CFAR is already color. And also this other one where we can see that the number of bits also grows, and it has many more classes. So the architecture, depending on different architectures that you might run into, like the ones that you have here or any others, the number of weights that you have also grows quite a lot. For AlexNet, you have already 61 million weights. And the number of multiply and accumulate operations that you do per image is already almost in the billions. So digging into a little bit more detail into what exactly this means. So in deep neural networks, there's a lot of matrix multiplying going on. So here we can see this this illustration where you have between two layers. In this case, it's just between the first and the second, but this goes on for each of them in the forward pass. You have to do a multiplication between the activations to get the activations out of the input activations and the weight matrix. So the colors here are mapped. What you get to the right, this vector to the right, is essentially the multiplication of this blue vector and the red matrix. And for back propagation, this is essentially the same, but in the other direction. So you have to do all this math all over again. So this is a pretty well-known image where you can see essentially what's going on, convolutions, subsampling, then the fully connected layers, similar to what we had before. But here we can see exactly what's going on. This is a 6-dimensional loop. So it's a for loop. That's, this is the first one for the output map, the second one for the input map. This is for pairs of pixels, so this counts as 2. And this is another one for each kernel elements, pair of kernel elements U and V. So this is a six-dimensional nested for loop, which anybody who's done any programming can see that that's quite costly, right? And our RNNs, recurrent neural networks, also they don't have all of the convolutions that I was just mentioning, but they also have these dense matrix multiplications going on because the activations in previous layers also influence further on. So you don't have the convolutions, but you have other things to worry about. There are, of course, apart from the multiply accumulate operations, you also have, as I briefly mentioned before, these pooling operators, ReLU or any other nonlinear functions. Those also carry their computations and they have their cost, and of course weight updates as well. So efficiency metrics are pretty important. So you have speed, which you could measure in something like number of inferences per second, but you also have these other ones, energy, for instance, inferences per joule, where a joule is a watt per second. And this is, of course, related to power consumption in the sense that you might be, paying for power because, that's what power is something that you have to buy, but also because it's what affects battery life, of course. So you also have then inferences per second per dollar, percent, or whatever the unit of cost you want to use. So all of these things have a pretty large impact into the whole training and then deployment efforts. So what can we do to make things better? This is a pretty good question. There's a lot that has been going, a lot of effort, a lot of research and development in different areas, ranging from hardware to distributed systems to better algorithms. So essentially, parallelization can go a long way because there are a lot of things that you can do if you have more than one core available. GPUs, of course, have been, in the last more than 10 years now, they have been the basically the stars of the show for a lot of optimizations. Quantization, which is essentially what I mentioned today, reduced precision. Compression, this has been also a pretty old technique from the 90s. I think Jan LeCun published the seminal paper on this, where you can try and get rid of connections that are not being used, or they're not being participating a lot in the computations. Of course, there's also better algorithms like fast Fourier transformations or Winograd convolutions. This is essentially math and engineering research going into these things. And also similar to GPUs, but more special purpose hardware are the application specific integrated circuits called ASICs, or field programmable gate arrays called FPGAs. These are also can be very, very useful if you have special purpose things that you want to deploy, right? So if you want, I don't know, some specific image recognition running on a specific video surveillance system, then you can develop one of these and you'll get some good advantages out of that instead of using general purpose hardware like CPUs and GPUs. So parallelization in hardware will unfortunately only go so far. This graph is also sometimes titled the end of Moore's law. I don't know if you remember, if everybody here remembers, but up until essentially here, you can see it happening with the number of logical cores in black. You can see that it was just one, right? There was this is in like consumer computing. So up until the mid 2000s, every PC had just a single core, but in the mid 2000s, it started going up where you could have multi-core CPUs with different, physical cores, logical cores, the explosion of Intel, i5, i3, i7 processors. AMD did the same thing. And you can see that this is pretty, it's pretty interesting to see how it coincides with single thread performance starting to go it had like an inflection point there, like not an inflection point, but like the curve started going, not growing so fast, right? So essentially what was going on is that the Moore's law, which was originally formulated as the number of transistors on a chip roughly doubles roughly every 2 years, that kind of kept going. But up until that point, there was like an understood equivalence between number of transistors on a chip and the speed of that chip, right? So what started happening is the single thread performance, like I was just mentioning, took a turn there for you're still getting more, but not that much, and it seems to be topping off out at 10 to the 5 here. So the same thing with frequency, up until that time, it was pretty common to see frequency going up as the years went by. And the same thing with power in watts. So as I was saying, parallelization in hardware will help a lot, but it will only take you so far. So we have also the possibility of doing compression and quantization that we're going to focus on in this lecture. Compilation also, and you can also, interestingly, there's a lot of research in the last few years on applying AI to optimize AI, like a meta training of AI models over this. So you can have what's called hardware awareness, and you can make the best out of the available hardware. So this is called acceleration research. All right, so as I was mentioning, this lecture is going to be specific on binarization, but since binarization is simply the extreme form of quantization, I'm going to spend a little bit of time talking about quantization, so it generalizes, right? So if you, instead of going just manipulating binary, so just bits, you can also do like 4-bit, 8-bit, 16-bit. So a little bit on on quantization then. In the context of deep learning, which is what this course is essentially about, quantization refers to the process of reducing the number of bits that are used to represent some value. We'll see in this case, our values are going to be weights and activations, but it can be essentially anything else. The term, I think, originated in, like many things, in signal processing, where they wanted to simplify the representation of an analog signal and see how many bits were needed to really, carry the information that was necessary. So standard precision nowadays, there's we'll see this in a bit, but there's an IEEE standard for this. Standard precision, there's essentially an agreement that it refers to 32-bit. So that's where double precision comes in, quadruple precision if you really need it. But if you just refer to a floating point number, you're talking about a 32-bit value. And as you can see here, it has a lot of precision there. 8 bits, you still you can still do a lot with 8 bits, but you can already see the difference in the number of possible values. 4 bits, it's just 16 values. 2 bits, 4 values, and extreme have only 1 bit. So the intuition from the signal processing, and it's essentially the same thing here, is that you have something very smooth and you're going to replace it with something not quite as smooth. It could be very, very limited, but something like what we see here on the screen, it might be more than enough to represent what you need, like maximum and min values, like frequency and that kind of thing, in the case of signals. So I'm assuming that everybody knows that they have been, I guess, through a computer organization class, or if not, then this is a crash course on this. Integer versus floating point representations. So floating point, like I was saying in just now, is 32 bits. Usually 1 bit is dedicated for the sign of the number. So if it's positive or negative, 8 bits for the exponent, and 23 bits for what's called the mantissa. So what's essentially, it's the mantissa elevated to the power of the exponent, and then with the sign, the corresponding sign. And floating point 16 is 5 and 10 instead of 8 and 23. So what this really gives you is a really broad range. So FP32 gives a really broad range. So you can represent numbers from 10 to the minus 38 to the same value but positive. And the accuracy, there's a nice graphic on this, on what this means, is very, very good. For floating point at 16 bits, it's still pretty good. You take a huge hit in the number of the range. Accuracy is still pretty good. For integers, so 32-bit integers, 16 and 8, it's much simpler because you just have, you're not representing any real values or anything like that. So you just have 1 bit for the sign and the rest for the number. So this is the range that you get. So 2 times 10 to the 9th is essentially 2 to the 31 power, right? And accuracy, of course, is 1/2, because since you can't represent non-integer numbers, if you have decimal numbers, then at most you'll be off by half, right? By 1/2, because you have to round it to the closest representable number. So this is the graphic I was talking about. Floating point numbers are not evenly distributed. So they have, this is an artifact of how they are represented, and this is how they get the good mix that they have between precision and range, and then the floating point. That's essentially where the magic happens. So you have to be conscious that a lot of numbers, this is what's being depicted here, a lot of numbers get mapped to the same value. So things can get weird, like this meme is showing. You're saving this value 0.1 and you read it and you can get something like this, right? So this is, it's not always going to happen, of course, but this type of thing might happen. There are other jokes like this. I always like to throw in an XKCD joke for you. But also this other, not quite that funny. It's not a joke, but it's the combinations of things that you have are not always what you might expect. So I'll leave this for inspection later, so I don't spend that much time on this. So what you have is integer numbers. They have this, they're pretty simple. Like I was saying, if you have 31 bits, then you can represent from 0 to 2 to the 31 minus 1, and the same in the other direction. But in floating point numbers, you have to deal with things like underflows, things that are too small to represent. Then you have your expressible positive numbers, and then you can also run into positive overflows. And the same, of course, on the other side, since this is symmetric. Here, if you're interested in playing with this sort of thing, I prepared a couple of examples just to show what this is about. Here's the link. I entered this number just to show, it's a pretty big number, but I threw in a 2 there. And then the value actually stored in the float is this one. The error due to the conversion is 10,000, so it's more than 10,000 off. But in such a huge number, that's probably not a big deal. And the same thing might happen to you if you store something like this, right? Like a 0.9999 with a lot of nines, it'll just be stored as 1, right? And the error due to the conversion in this case is quite small, but it's there. So you have to be careful. A little bit more about floating points, this time in closer to hardware. So the additions of 8-bit integers or 16 and 32 floating point additions, here you can see the difference in picojoules, which is a very, very small unit. But if you're doing millions, billions, or trillions of these computations, it really adds up. So it's pretty interesting to see what the relationships are between these numbers, especially if you look at the difference between the floating points and the integers. And the same thing for multiplication. Compare multiplying an 8-bit number versus a 32-bit floating point number. It's impressive. And also very interesting is, well, I have this on SRAM and DRAM in the next slide, but also very, very interesting is the relative area costs. So in square picometers, again, very, very small, but this is area on the chip that you have to dedicate to implement these operations. So you can see again how this grows, especially for 32-bit floating points, additions and multiplications, which is essentially what's going on with the multiplication and accumulation operations. So the staying local is also very, very important. This is what's going on here. So SRAM is local, is on chip. So this is what's going on with at the level of kilobytes in modern hardware, and you only pay 5 picojoules a word so a word would be 64 bits in most modern systems. But then you have also on-chip SRAM, which is bigger, the cache storage that you have, but it's already 10 times more expensive in terms of power. and then another more than 10x jump when you have to go to RAM. So RAM is very, very fast compared to disk, but it's pretty bad compared to registers on your chip. So you have to be very careful if you're really being, sensitive, careful with how much power you're spending. So of course, all of this is essentially leading up to what are the benefits of quantization. So of course, memory usage is perhaps the most obvious one. So if you have 32-bit weights versus 8-bit, it's going to be a 4x difference. If it's only 1-bit, it's going to be a 32x difference. Power consumption, we already went through that, but you can see that you can reduce by 18.5x your energy, your multiplication energy used, and 30x for additions, and also memory access is 4x. Latency is also might be very important, especially on modest hardware. With less memory access, you have simpler computations, and then latency can be reduced, especially if you're looking into something like near real-time systems is very important. And of course, the silicon area, essentially space is always at a premium, so you have to be careful what you use it for. So again, you can have very impressive reductions in that dimension as well. So the analogy of quantization here in bits per pixel in this animation is pretty interesting, because you can see 24 bits the standard image. With 8 bits, you can see the loss, and with 1 bit, of course, you only get black and white values. It's essentially the same thing that was going on with that signal that was, looked like a staircase instead of a smooth signal. But in general, you're going to run into two sources of error with quantization. The first one, that's why I spent so much time talking about floating points and their details. The first one is called the rounding error, and the other is if you are clipping, for instance, a standard precision floating point number to an 8-bit integer, then you can only represent minus 128 to plus 127, and if you have something that's outside that area, like you have here, you're going to run into what's called a clipping error. So you have to be really careful with these things, and this is where a lot of the further optimizations come in for neural networks, as we will see. So there's a little bit more detail on this. It's essentially the same kind of thing with a little bit more detail. So you have the rounding, which will depend on specifically what format you're going to use with B bits in this case, and clipping errors also depending on your Q min and Q max values that you can represent. All right, so after that pretty long intro, which I think is important to understand what everything else is what is happening with BNNs. So binary neural networks, as I was saying, essentially you're transforming your weights and your activations. Instead of having floating point, standard floating point 32-bit values, you have to reduce them to just a single bit, so just 2 values. The important thing to know, that sounds like it's impossible, but the full binarization will only really be completed after training. So what's I'm going to focus on in this lecture is called quantization aware training, where once you're done, then you can drop your full precision values and keep the binary ones. There's also an early model, I think it was the first ever attempt at this in 2015, that only binarized the weights and kept the activations in full precision. But it's now standard if you want to call it a BNN, you really have to binarize both things. So let's see a few of these of the basic concepts before seeing a little bit more of the details on how they are built and trained. So the first thing that is pretty interesting is this. So I spent quite a lot of time talking about multiplication and addition. So in particular, multiplication, you can implement multiplication essentially by using an XNOR gate. So XNOR is essentially XOR, exclusive OR, plus an inverter gate. And this is explaining why binary neural networks, instead of using 0 and 1, they're going to use -1 and 1. So if we map 0 to -1 and the 1 is still 1, then if you can quickly check this table that if you multiply these values, you're going to get the same as XNOR. So you simply can implement multiplication very, very cheaply with XNOR gates. And as we will see in a bit, there's also convolutions, which I mentioned at the beginning. All you need is XNOR, so the multiplication, and then what's called pop count or population count, which is another very, very cheap operation that typically comes in modern hardware as part of the basic instruction set. So they're very, very optimized for power consumption and speed. And with both of these things, you can implement your own convolution. So this is what it looks like. If you have 32 bits and you have to multiply and then do essentially a convolution, then you can essentially get rid of the multiplication and the sum and just do XNOR and pop count. So here you can see that you get a -5 because remember the zeros count for -1s. So you have 1, 2, 3, 4, 5, 6, 7 zeros and 2 positive ones. So you get a -5. So then the cheap MAC multiplication accumulation operations are essentially instead of doing it with 4 times 32 bits and paying the costs that we were seeing, you could just do simply with bits, do XNOR and then pop count. This is just a trick, 2 times pop count minus bits to do it quicker, because times 2 is just a shift in the registers, and that's very fast as well. And you can do the difference as well very fast, and you get the same result. So this is essentially what's going on under the hood. In a binarized convolution layer, then with a little bit more detail, just so we can see everything that's going on. Here, this is a pretty nice example where you have the full precision matrix here, having to do a lot of operations just to get this value. You have to do all of this. And as we will see, if you just do a sine function to get the binarized values, then you get 1-bit activations, 1-bit weights, and then the outputs obtained, like I said just now. So you have your activations, your weights, you multiply them with XNOR, and then do pop count. So quantization aware training, we finally get to what we were hoping to arrive at. Essentially looks like this. So you're going to see in the forward pass where weights are binarized, but in the backward pass, you need to approximate the gradient. So can anybody tell me why this might be the case?
Why would you need? Yeah.
Maybe because the stochastic gradient descents need floating point numbers to get more parameters and explore more weights, so that the model becomes more regularized.
Yeah, but why essentially? If you have something like this, you're binarizing with the sine function. So on your way back, what is gradient descent or stochastic gradient descent or whatever algorithm you're doing, what is it doing essentially? What is it calculating?
Gradients.
Gradients, exactly. Does this look like a differentiable function to you? No. It's going to be, the gradients are all going to be zero if this is what your function looks like. So what you run into is essentially you're going to get a zero derivatives for everything, right? So what BNNs need to do is estimate the gradient on the way back in order to be able to do to train. Otherwise, it wouldn't learn anything. So the most basic thing that you can do is called a straight through estimator. It's called an estimator, essentially like in the sense of statistics, right? Where you're trying to estimate a value that is subject to random events. So in this case, a straight through estimator is really simple. All it's doing is simply setting all the incoming gradients equal to the outgoing gradient. So you just disregard the derivative of the function. So on average, this is what is interesting. On average, it's a pretty good estimation that is very easy to implement. How do you do that? With something called the hard hyperbolic tangent function, which looks like this. And essentially, it's very simple to implement. It's just essentially the identity function, the identity mapping, and the derivative that you get is plotted here. So it is differentiable. I also plotted here the hard sigmoid function just so you wouldn't get confused, because the hard sigmoid function is also hard. It's in the original paper as one of the functions that you could use instead of sine. So it has essentially the same shape, except that if you pay attention, the range is between 0 and 1, whereas the hard tan h function is between -1 and 1. All right. So the binarization of the weights, then you have to keep full precision copies of weights throughout training. So it's necessary for there to be able to do the training correctly. And then, so otherwise you would never be able to accumulate small changes in the gradient without losing precision terribly. So essentially, as we will see, all of this is going to map into slower learning, but in a lot of cases without losing accuracy. So after training, then you can keep only the quantized weights, and that's what you're going to use for your inference. So in a little bit more detail, just a little bit, what's going on then is that gradient descent doesn't work with binary values. Like I was saying, all you're going to get is zero derivatives. So you keep real valued weights, because binarized weights cannot be updated during gradient descent. You just have nothing to work with, essentially. So they're kept and updated during training with this scheme here. We have you clip the values so you can calculate the sine function, and then on the way back you do the straight through estimator. So this is done, the clipping is done so that you can reduce mismatches with the binarized weights. And then once the training is completed, like I was saying, you can throw away the real weights and just keep the binaries. And then that's where the full benefit of the cheaper computation is going to pay off. So on the way back, then you have the sine function that was sorry, not on the way back. For this was for weights and this is for activations. They're done in a similar way. You have the sine function, and then you don't need here the clipping. You have full values, also full precision values maintained during training, and then you do the straight through estimator that also implement some clipping here so that through the hard tangent function that I was showing before, and it cancels the gradient steps when the activations become too large. So essentially, what is going on is here we have the schematics of the first layer, the input layer, and then in general you're going to have something like this. So the layer you're working on, the previous one, and the next one. So in order to binarize, all that's going on is essentially this: you're adding like an extra computation there, where you implement what we just went through. Good thing is that nowadays there are quite a few libraries that take care of all the heavy lifting, but it's not even that heavy a lifting. That's what I'm saying. It's not that really that difficult. So the elegance of the model is really it's pretty impressive how by just modifying this part of the structure, you can reap all of these benefits that we were covering before. So the core concepts, again, in this nice graphic from a recent survey, is the sine function. You have the zero derivative issue on the way back. That's why you have the it's called approximate sine, or the straight through estimator. The derivative looks like this, and essentially you can take care of all the training operations. So for quantization, instead of, this is the same kind of schematics, but without this is considering that you might have lower precision instead of binary. So it's the same, essentially the same thing. This is not only depending, it doesn't just work for binarization, it also works for quantization in general. So quantization essentially is the most extreme form of binarization is the extreme form of quantization. So the results, this is perhaps the most impressive thing, apart from all that hardware stuff that I was talking about. Some first results, this is from the original paper in 2016. You can see just by looking at these loss curves that the BNNs are much slower to train. So the baseline, the full precision baseline, you can see that it immediately was training on the CFAR 10 task. And then a couple of variants of BNNs, and they are they're slower, but they get there pretty fast anyway, right? And the validation errors also, you can see the same sort of relationship between the curves. What is really impressive is the impact on speed, which the authors, again in 2016 from the original paper, they got a 23x speed up on large binary matrix multiplications using a specific NVIDIA GPU, 3.x faster than the cuBLAS library, and 7x faster on MNIST CNNs. So this is pretty impressive here, and this is not a very nice way of combining graphs, because the bars look exactly the same here, but it's a matter of scale. It's pretty much the same accuracy. It's not exactly the same, but it's on par in terms of accuracy. So it's barely affected. So these are results from the original paper, top 1 and top 5 accuracy on the ImageNet data sets, because these results are for the CFAR tasks. They're not that difficult. So ImageNet is much more difficult, and there the results are not that impressive. So it's top 5, you get a 60.1% accuracy, whereas the state of the art at that time was 80.2. That's using AlexNet. And with GoogleNet, it's similar relationship. You get 69.1, and state of the art was almost 90 in that sense. 1 year later, there was another NeurIPS paper that achieved performance almost on par with state of the art. So in that sense, it really did make up for the differences here that we were observing. So moving on to what else has been going on in the BNN literature, we can see. So I prepared an overview on based on a couple of recent surveys, where we can see essentially all of these dimensions. First of all, the quantization error minimization. Remember that I mentioned that there's information loss going on with rounding errors and clipping errors. So trying to minimize that. Loss functions improvement, where you can add regularization, distribution, different distribution loss, better gradient approximation. So to solve this zero derivative issue, so what we saw was just the basic approach. Of course, there's always the last two, which are fiddle with the network topology structure, so we can improve and optimize, see if any specific network topologies work better with BNNs, and what's called strategy and tricks that you can always come up with. So we won't go into a lot of detail, but this is a pretty thorough survey up to 2020 at least, where we can see a lot of these things. First of all, these tricks here, where you can see that structure transformation is the first column. Op is the optimizer that you can use during training. This is these are pretty well-known optimizers. We'll go through them in just a bit. Asymptotic quantization is another interesting trick that not a lot of works have ventured into, but it's pretty interesting what they do. And then gradient approximation that you can see in the latter ones that shows up. So the other strategies that we were mentioning are, in this case, the authors chose to essentially classify the approaches based on these. So the first ones focus more on minimization of quantization error, then the network loss function improvement, and then the reduction of gradient error. So for structure, here we can see that the legend says that RB stands for reordering the batch normalization layers, and RP is reordering of pooling layers. So there's a lot that you can do. There's research into optimizations that you can come up with. There's also another one called widening. It's one of the called the wide reduced precision networks. Essentially, if you pay attention when you carry out these operations, you can do better essentially. So this is what's been shown here in the 2016 was a pretty big year for binarization. You can see this XNORNet, and then there was another model called XNORNet++. I think it's probably in this table. Yeah, there it is. XNORNet++. Essentially, they focused on moving batch normalization to the beginning. So blocks in XNORNet look like this, and then the binarized activations and the convolutions, and then the pooling. So again, this simple change had a pretty big impact. And just looking at SC, what was SC? Shortcut. Also, shortcut means that there are ways in which you can communicate layers between them so that they can implement quicker training, essentially. So for optimization, this is essentially the same thing that goes on in deep learning in general, where you have the different possible optimizers. So A is for Atom, one of the most well-known ones. Eta Max AM, RMS Prop are the most well-known, and you can see that there's been a lot of research in how these things combine with the other tricks. So just as a refresher, optimizers, they have a couple of nice animations like this. You can see they're essentially all trying to be quick. Essentially, you can see here that SGD is the stochastic gradient descent is the slowest one to reach the goal, whereas the others in only a few iterations. Like one of these, momentum and nag, they do some weird trajectory, but they get there pretty fast, and the others are better. There's also the possibility of getting stuck in saddle points like this. So essentially, there are tricks and optimizations used to maximize or minimize loss in the fastest possible way. Also trying to not get stuck in any place. Like again, this is SGD being stuck in the saddle point, and also the others, actually. A lot of the others, except for these, they get stuck for a while, and then they finally get loose. Adaptive quantization. This is a pretty interesting one, where you can see that the quantization, you can do it in a sense in stages, instead of like going full binary in one go. Then you can essentially reduce the precision with in steps, in such a way that we'll see this in a bit in the next. This is more because this is from the paper where they do both adaptive quantization and gradient approximation. But essentially, what you're doing is you try and, with traditional binarization, just take the sign and you get something like this, where this is computing the entropy value, and you can see that it loses a lot, where if you do a more balanced effort, then eventually you can do sine again, but now here you preserved much more of the structure, so you get more out of your weights and activations, essentially. So without going in one step to the sine function. And lastly, we have gradient approximation, where instead, similar to what was going on with adaptive quantization, instead of just using the identity function and clipping like we saw in the early models, you have your original curve like this. It's much smoother, and instead of applying the sine function, you transform it and try and get within the bounds, and also arrive at, I don't know if you see it on your screen, but here you can see that the edges aren't as sharp, so you can get a much better approximation to your original curve. So compare this center figure with this one, and then with this one. So your errors are going to be smaller. And that's a lot of what the ladder works. So the most the newer works are focusing on. So there's a lot of research on this. Is from again from a 2023 review that essentially they go through a lot of different functions that you could use instead. So the most basic one that we saw is the sine function. You can see here the derivative, the explanation that I was giving before. It's just going to be zero all everywhere except for on zero, which is infinite. You can have on the backward training, you just have the straight through estimation, but there's also a lot of different functions that you can play around with and see if they work better. So the authors show essentially 9 different approaches where you get different performance when they're applied during the training process. It's also interesting that there's another dimension that you have to consider in conjunction with the other tricks that we've been going through, and that's why I guess there's so many different approaches, because there are different ways to combine these things, and unfortunately, even though there are a lot of good results, there's not a lot of research in the sense in trying to understand what applications are best for the different variants of PNN. So this is reminiscent, of course, to the plurality of activation functions that we have in neural networks nowadays, where you have things like ReLU, leaky ReLU, PreLU, all these variants of activation functions that you can fiddle with to get better results in some cases. So as a summary, here's again the table, and we have quite a few approaches, and this is from 2020, so it's not capturing what happened in the last few years, but this survey that I left on Canvas as well for you is available, and it's from this year. So some results for these, only a few of these is from another review from 2019, just to get a little bit of a taste of what kind of results they get on ImageNet. So on the more complete test bed here, we can see the full precision. Again, this is comparing different topologies like AlexNet, GoogleNet, and different variants of ResNet. Top one is not that great, so the interesting values appear here at top 5, where we can see that some of them are reaching, like I was saying, like ABCNet is pretty good. It's on par with full precision ResNet 50. Other ones aren't that far off. They're at 88, 85, so it's still pretty impressive. Again, ABCNet is one of the best, at least until 2019. And here we can see the different topologies that they were implementing. So you have learned parameters, signs with threshold. This is what I was talking about today with one of the models uses this ReLU function, which is basically a parameterized leaky ReLU. Instead of fixing the parameter, you can learn it without a huge impact on the training process, and the different regularization techniques that they used. Another pretty interesting figure is this one, where we can see what the top 5 error percentage in this case, not instead of these or accuracy errors. This is top 5 accuracy figures. This is top 5 errors, so lower is better. The dotted line here represents humans on ImageNet, human performance. So you can see 2014 to 2015 was the year where this task was essentially where neural networks started beating humans. 2016 is where the early models appeared. They were not doing that great, as we saw with the early models, but already in a few years later, we were seeing much better results. So we're still not at the point where, or actually ABCNet was, but yeah, I don't know why they're not including it here. With we're not at the point where we can get that low of an error, but it's getting better. Well, actually, this is a different challenge. That's why they're different numbers. All right. So to conclude, we first focused on binarization, seeing how quantization in general, but binarization in particular, has been shown to provide very, very important savings in terms of space, compute time, and power. And this might not seem like such a big deal on traditional systems, but when you're focusing on edge computing, or if you are very careful with how much power you're spending, or for example, if you want to be friendly to the environment and spend less energy, then it's also very important. So another advantage that I didn't cover here, but it's also very interesting, is that binarized neural networks are more robust to adversarial attacks. So the intuition being that small changes in the input, which is what adversarial attacks are based on, have less of an effect on network activation, since discrete values are used. It's like you kind of get it for free because of what you're doing, right? You're reducing your space to such a point where the attacker doesn't have that much elbow room to craft, or at least not the same types of attacks will be the same. But I think there are works where they are shown to be vulnerable, but not as much. And what I was saying while I was going through all the variants is, though there have been many proposed models that are based on this idea, and they achieve good performance in different tasks, there is really more research needed in terms of matching them. Like, how do I choose which one to use if I have a specific application in mind? So with that, we're done.